Good morning, students. In this session, let us discuss about the balancing of several masses rotating in the same plane. So, as to the balancing of rotating masses concerned, there are four cases. Balancing of single rotating mass by a mass rotating in the same plane. Second, balancing of a single rotating mass by two masses. Third case, balancing of several masses rotating in the same plane. And fourth case, the balancing of several masses rotating in the different planes. In this session, let us discuss about the third case, balancing of the many masses which are rotating in the same plane. So, consider the diagram. There are four masses M1, M2, M3, M4, which are rotating about the center point O with a different radius of rotation. So all are at the same plane. Let us assume the mass is perpendicular to the plane of paper. So the mass M1 exerts a centrifugal force Fc1. Similarly, M2 mass force Fc2. Mass M3 generates a force centrifugal force Fc3. Mass 4 M4 Fc4. So we know the formula for the centrifugal force of a rotating mass is Fc equal to m omega squared r. All the masses rotating at the same angular speed. So for analysis, we may neglect the angular speed omega. So Fc1 is equal to m1 r1, Fc2 equal to mc2 r2. Similarly, Fc3 and Fc4. For balancing this problem, there are two methods involved. One is the analytical method and second is the graphical method. So let us discuss one by one. So the mass 1 with radius of rotation R1, mass 2 with the radius of rotation R2. Similarly, M3 and M4. So we have to balance the four masses by employing a mass which we should give the centrifugal force which should be equal to the resultant force created by the four rotating mass, so that the forces are equal and opposite direction, so that the system will be in perfect balance. That is the idea behind it. So let us discuss about the analytical method. First, analytical method. Each mass is hit at an angle to the horizontal. For example, the mass 1 is at angular position of theta 1 from the horizontal OX. Similarly, mass 2 at theta 2, mass 3 at theta 3, and M4 at theta 4. So let us dissolve the forces horizontally and vertically. So the horizontal component of the forces is first mass M1 R1 cos theta 1. For the second mass M2 R2 cos theta 2. Similarly, it's for the four masses. And similarly, vertical component sigma V equal to M1 R1 sin theta 1 plus M2 R2 sin theta 2. So it goes on up to the number of masses involved in the system. Now, the resultant force of the four masses is square root of the horizontal component, square component, and the square of the vertical component. So it is called the resultant force Fc. So by idea, we have to keep a mass which should balance the four masses. So the balancing mass also should exert a force which should be equal to the force Fc. That is the idea. Now we also, by which we can know the centrifugal force of the balancing mass. Now, next we have to identify and calculate the angular position of the balancing mass. So we know the tan theta equal to vertical component divided by horizontal component, by which we can calculate the theta. So the balancing mass is also can be located in the space diagram. So now equal to the, we can equal the FC resultant force to the balancing mass, that is M into R. So M is the mass of the mass to be balanced with this rotation, radius of rotation R, from which we can calculate the resultant force of the balance, that is all masses, and also the balancing mass to create the resultant force FC, by which we can also calculate the mass and the radius, and also by the tan theta equal to sigma v divided by sigma h, we can locate the position of the balancing mass also. So on the, from the diagram, we can identify the OM is represented by this diagram. So it is in the opposite direction, so that it can counteract the effect of the forces created by the four masses, so that the system will be in perfect balance. That is the idea. So it is the analytical method by which we can estimate the value of the mass, radius of rotation, and the angular quotient. Similarly, can also be found by the graphical method. First, we have to draw the vector diagram. So all the forces are, centrifugal forces are represented as a vectorial form. So we know the position of the each force exerted by the individual mass and also the position. So mass 1 exert a force Fc1. So we have to fix a scale. Then you draw AB vector, which is equal to the Fc1 created by the mass 1. So the AB is parallel to the line OM1 in the space diagram. Similarly, for the second mass, draw vector BC equal to the magnitude of Fc2 with the scale fixed. Similarly, for third mass, draw CD, and fourth mass DE. So from A to E, we can draw the vector diagram. Now, as per the law of force of polygon, the closing side always represent the resultant force of the forces involved in the system. So join E and A. So the E and A represent the resultant force of the four masses, that is Fc. Now the direction is opposite to the other three forces, so that the arrow mark is marked here. Now from this vector diagram, we can estimate the resultant force value and also the orientation of the balancing mass to be fixed in the system. So comparatively, now we can assume compared to the analytical method, the graphical method is very quickly can be calculated, the position and the estimation of the centrifugal force. Now we can solve one problem in this case. Four masses M1, M2, M3, and M4, which have the mass of 200 kg, 300 kg, 240 kg, and 260 kg. So with the rotation 0.2, 0.15, 0.25, and 0.3 meter respectively. So four masses are given, and with the radius of rotation. So the angle between the successive masses are 45, 75, 135. So the angles are given with the successive masses, angular distance between the successive masses. So we find the position and the magnitude of the balancing mass required if its radius of rotation is 0.2 meter. Now for these masses, we have to calculate the balancing mass, that is M, but the radius of rotation is given. So our objective is to only find the value of the balancing mass M. So the data are given M1, M2, M3, M4, and the radius of rotation R1 to R4, and the angles are represented in the diagram from the same reference. So for that, now we can look at the diagram. First mass is kept horizontal. So for our calculation, all the angular position of the masses are taken with reference to the first reference masses. So it can be laid or drawn horizontally, first mass. So as per the question, the successive angular descents are marked. So from that, the theta 1 is 0, and second mass is 45 degree to the previous case, and third mass from the previous is 45 plus 75, that is 120, and fourth mass is 120 plus 135, that is 255. So all the masses are denoted with angular distance from the same reference horizontal, the first line. So the balancing mass with the radius of rotation 0.2. So now our aim is to find the balancing mass value m. Now we can draw the space diagram. So there is no scale needed for the space diagram, but the only requirement is the position, angular position of the different masses are to be located accurately using the protractor. Now we can calculate the centrifugal force as we already discussed it. All the masses are rotated in the same angular speed, so we can omit the angular speed, so it won't affect our analysis. First mass m1 r1, second mass m2 r2. Similarly, for all masses, the centrifugal forces are calculated. So in the analytical method, first horizontal component, as we know, first mass m1 r1 cos theta 1. Similarly, for all the masses, so the horizontal component summation is 21.6 kg meter. So in the resolving the forces vertically, for the first mass m1 r1 sin theta 1. So similarly for the up to fourth mass, so the value is 8.5 kg meter. So the resultant force is square root of horizontal component, square of the horizontal component plus square of the vertical component. So it comes 23 kg meter. So the resultant force represent it is the net resultant force coming out of the four masses revolving in this system. Now we have to keep the balancing mass. The mass also should exert a centrifugal force equal to 23.2, but in opposite direction. That is the idea. So we can equal the balancing mass centrifugal force is m into r. It be equal to, that is 23.2 FC. From that, already the r is given, so we can calculate the m 116 kg. This is the value of the balancing mass to be fixed in the system. Now the position of the balancing mass, tan theta equal to vertical component divided by horizontal component. So the theta is 21.48. So all the angular positions are marked from the horizontal. Now already the first mass is horizontal, so we can extend. So it is 180 degree plus this degree is 21.48. So 180 plus 21.48, 201.48. So 180 degree from the first mass. Again here, now we can draw the angular position of the balancing mass 180 plus 40, 21.48. So totally 201.48 degree. So by the analytical method, we can estimate the value and position of the balancing mass. Again, similarly, for the graphical method, now we go to draw the vector diagram. Now we know the value of the centrifugal force exerted by each mass m1 r1, m2 r2, now m2 r3, m4 r4. So by suitable scale, we can draw the vector diagram for the force. That is, we draw the force polygon. So AB represent the centrifugal force equal to the value of magnitude drawn with the suitable scale. Similarly, BC for M2, CD for M3 mass, and DE for M4 mass. Now to join O and A, this is the closing side of the polygon. So the side EA vector represent the resultant of all the forces exerted by the four masses. So it's also the value of the balancing mass exerting the force. And also we can easily know the position of the balancing mass. So we can draw the balancing mass angular position parallel to the vector AE. So we can measure the vector AE, by which we can estimate the
mass of the value. Now, from the diagram, the vector EA represents 23 kg meter. Already this is equal to the mass into radius. Already radius is given. So the unknown parameter is only m. So m is 115 kg. So the mass of the balancing mass 115 kg, which is similar to the value obtained from the analytical method. So also the vector AE. So we can easily draw the angular position of the balancing mass parallel to the vector AE. So by measurement, it shows the value 201 degree, which is also same to the answer obtained from the analytical method. So students, I hope you have understood the balancing of several masses rotating in the same plane. Thank you.